Hey guys, welcome back or welcome. My name is Mr. Kim, and I am going to be going over the FRQ questions from the January 21st, 2025 administration of the New York State Regents in Chemistry. So let's get started. Number 51, state in terms of electron and energy states how the light emitted by excited boron atom is produced. Well, how do you answer that? You should know at this point that light emission is from the when the excited electrons drop back down, right? So what are we going to write on this one? We're going to write that um, when boron is excited, um, one or more of its electrons um, is not is jumps, right? Jumps to a higher orbital as this excited electron returns to its ground state. Energy is released in a form of light. Okay. All right. So let's look at the second question. Second question says, the atomic mass and natural abundance for two naturally occurring isotopes of copper are shown in the table below. Um, show numerical setup for calculating the atomic mass of the element of copper. All right, so it says show a numerical setup, right? It doesn't say to actually calculate. So that means we just set up the problem. So how do we do that? It's actually atomic mass times the natural abundance as a decimal, right? Which means we're going to move the decimal places over like this, right? So at 62.93. So it's 62.93 units times its abundance in percentage is 0.6915, right? And remember, it's the sum of that. So the next is 64.93 units times 0.3085. What happens if you forget the U for the units? I don't think they're going to care so much. Please make sure you circle the correct answer. Onwards. A technician determined the percent natural abundance of copper 65, that's this, their sample to be 31.47%, unlike the 30.85%. Determine the percent error for this percent natural abundance of copper 65 compared to accepted value. All right, so what are we looking at? We're looking at it's what? Difference divided by OG times 100, right? That's right? It's the difference over the original, which is going to be what? 3147 minus 3085, right? So it's going to be 31.47 minus 30.85. That should give us the difference. Divide by 30.85 times 100, right? And that should give us 2.0097. However, it's 4 sig figs, which means that we're going to round at the 9. So the answer is going to be 2.010, right? So I'm going to put 2.010. Some of you guys, please make sure your decimal is nice and visible. Okay, let's go to 54. 54. The element beryllium, magnesium, calcium, strontium, barium are located in group 2 in the periodic table. These group 2 elements have both similarities and differences in their physical and chemical properties. Based on the location of group 2 elements in the periodic table, state the element classification of these elements. Let's go. So if you go here, beryllium is located right here. This is the group, and we know this to be what? We know this to be the alkali earth metal. Now, it says city element classification, which means that you could probably also get away with by saying metals versus not metals, right? That should be also okay. 55. Explain in terms of electron shells why the atom of atomic radius of calcium is greater than atomic radius of magnesium. Let's take a look. Calcium is here, magnesium is here. So what do we know about this? Well, it's easy. If you look at the electron configuration, right? What do we notice? We notice that calcium has one extra shell compared to that of magnesium, right? So we can say that calcium has an extra shell of electrons, making its atomic radius larger than that of magnesium. Okay. Okay. Onwards. Number 56, state the general trend in first ionization energy for the group 2 elements, beryllium through barium, as these elements are considered in order to increase the atomic number, right? So a couple of things we need to understand. What I remember saying in class for you guys is you got to understand two things. One, what is the atomic radii trend first? Second, understand the definition of what ionization energy or electronegativity are, and then apply it to a radius. So let's go. So the definition of ionization energy, or the first ionization energy, same thing, is the energy that you need to remove an electron from that atom, right? So what do we know? If we're trying to steal an electron from an atom, who is it going to be easier to steal it from? It's probably going to be easier to steal from somebody, right? If that's a nucleus, somebody that has more shells, because that electron will be easier to steal because it's got more electrons keeping the nucleus busy from holding on to this electron, right? Conversely here, if the atomic radius is small, it's so close to the nucleus that it's going to be held really tight. So let's look at the atomic radius, right? They literally asked you in the previous question, they didn't ask you, they actually told you, right? That the trend, which means we know that as you go down, radius gets larger. So what do we know? That means that as you go down lower, the last electron is going to be sitting further and further out with more electrons between it and its nucleus, right? And therefore, the answer is, right? The answer is the, right? And also, go back and see what they asked. They said, state the general trend of first ionization energy. So you got to start with that. So you say the first, right, ionization energy decreases right? As one goes down a group. Okay? What else? The other way to solve this, which will take a little bit longer, is to actually physically look up these values, right? So let's go to beryllium. Beryllium is number 4. So if you go to the next page and look up 4, right? Beryllium is got a first ionization of 900, right? So beryllium, excuse me, beryllium has a first ionization energy of 900. And if you pick something like, calcium or strontium, let's pick number 38. What is 38? If you go to 38, you'll see that it's 549, right? So strontium is 549. And then you go to radium. Hello, radium. I forgot what the number was, right? Radium is going to be 88, or barium, they said, right? 56. So let's go to 56. 56, barium is going to be 503, right? So barium is 503. And if you can see, it goes from 900 to 549 to 503. And you can see that it decreases. Takes a little bit longer to solve it this way, but this is another way that you can say that it decreases, as you see here. Okay, let's go to 57. Number 57, diagram 1, this is a gas law, right? So what are some of the things we need to know for gas law? We need to understand the equation PV equals nRT, right, PivNerd? Compare the average kinetic energy of the gas molecules in diagram 1 to the average kinetic energy of the gas molecule in diagram 2. And what do we know about kinetic energy? In class, we learned that kinetic energy is directly related to the temperature, right? We talked about that. At a high temperature, things move faster. At a lower temperature, they move slower. And what do we know about these two temperatures? They are the exact, excuse me, same temperature, which means, what can you tell me about the movement of the gas molecules? They're going to be exactly the same. So you're going to say that, and let's go back. It says compare the average current. Okay, so you don't have to be really wordy, but you say the average kinetic energy will be the same. Now, did they ask you to explain or justify? They didn't. But if they did, right? So nowhere here it says to justify. So you're actually done. In fact, if you just write the word same in 57, I almost feel like they're going to give you the answer, right, for that one. But if they ask you to justify, it's because you would say that the two temperatures are identical between the two cylinders. 58. Determine the volume of the O2 in diagram 2 when conditions are changed to STP. Okay? So how do you do this, right? This is Boyle's law or ideal gas law, right? So what does that mean? That means if we go let's go to the gas laws, right? If you go to the gas laws, we see combined gas law right here. Okay, PV over T equals PV over T, right? So what does that mean? That means I know in class I said, hey, always do the labeling first and go find it. But in this case, because we know it's gas law, right? It's P1 V1 over T1 equals P2 V2 over T2. I'm going to go back here and I'm going to put in P1 V1 T1 P2 V2 T2, right? What do we got going? Initial conditions are right here, right? So it's going to be, this is going to be P1 V1 T1, right? And then so we have that, right? Which is these values. Well, what about these? These are STP, right? If you didn't know, right, what are they? Well, we want to know determine the volume. This is our unknown, right? But we know that standard pressure, right? If you didn't remember, it's 1 atmosphere or 101.3 kilopascals. Where do we get that from? We get it from here. If you go all the way to the front of the reference table, it is right here, right? Standard pressure in kilopascals, that temperature is that, right? So by taking those values, right? That's 273 kelvins, and pressure 2 is going to be 101.3 kilopascals, right? Because that's the STP. Got it? So I'm going to put in the work in the other place, all right? So let's go. I'm going to put some work down here, okay? So this is going to be number 58. It's going to be P1, V1, T1, P2, V2, T2, right? We know that this is going to be your X. This is going to be 101.3 kilopascals. That's from the front of the reference table. This is going to be 273 Kelvin. That is also from the front of the reference table for STP, right? So what are the other conditions? The original condition is 60, 1.8, and 300. So it's going to be 60.0 kilopascals, 1.8 liters, and it's going to be 300 dot kelvins. Am I right? Let's double check. And it is correct. So what do? We go P1 V1 over T1 is equal to P2 V2 over T2. And what are we solving for? We're solving for our V2, right? So since we're solving for V2, what do we have to do, right? We're trying to isolate this guy. So we're going to multiply both sides by T2 over P2, because that will allow me to cancel out, right? That giving us our V2, right? So we're going to do the same thing on both sides, right? So we're going to do the same thing on both sides. It's going to be T2 over P2. Now, if you remember, I said when you rewrite it, let's rewrite it. V2 is equal to, right? So this is all gone on the right side. It's going to be T2, P1, and V1 on the top, right? Like that, right? Over CP2, it's underneath P1. I'm going to write it like this. And then you got T1, I'm going to write it underneath T2 like that. Now remember, the reason I said that is because sometimes they ask you for just the work. Now, in this case, it isn't, but let's just plug in the value, shall we? So plug in the values, you get 273 kelvins times P1 is going to be 60.0 kilopascals. V1 is 1.8 liters all over. T1 is 300 kelvins times P2 is 101.3 kilopascals, right? And just like a good student, what I'm going to do is I'm going to go cross out our units, and the liters is what we're trying to solve for, right? And then if you plug this into your calculator, what are you going to get? You should get a value that is, let's see, 0.97, right? And is it 2 sig figs? Yes, it is, because 1.8 liters is 2 sig figs. And that is going to be in liters. So I'm going to go over here. I'm going to put 0.97 liters, and that should be the answer. Let's go to 59. Determine the pressure and atmospheres of the nitrogen gas in diagram 1. Now, don't overthink this, because what do we know in diagram 1? In diagram 1, pressure is right here. So what they want you to do is convert. Okay? So they want to convert from 600 kilopascals to atmospheres, right? To atmospheres. So let's do it. So 59, let's put the work for 59 over here, right? So it's going to be 600, right? 60.0 kilopascals, right? And what do we know? We know that if you go here, the unit, right, is this, right? It's right here, which means this means it's 101.3 kilopascals per 1 atmosphere, right? And it's vice versa, right? So now if I go here, I can do this, right? You want to go to ATM. So that means that you want to get rid of kilopascals and put ATM. And remember, from the first page of reference table, it's 1 ATM for 101.3 0.3 kilopascals. Okay, plugging the values in, you should get with 3 sig figs 0.592. So I'm going to write that in here. I'm going to put in 0.592, and we are done with this question. All right, let's go to number 60. The boiling point of sample of molecular compound is 80 degrees Celsius at standard temperature, standard pressure. The heat of fusion of compound is 127 joules per gram. All right, already when I see this, what am I thinking of? I am already thinking that heat of fusion, right? It's right here, except this is for water, right? So what do? There's an equation for that. If you go all the way to the back last page, what do we got? For heat, you got heat of fusion equation right here, right? Right here. All right, so let's go back and take a look. Compare the potential energy of the molecules of the sample before vaporization to the potential energy of the molecules after vaporization, right? So what are we looking at? We're looking at vaporization, right? So what are we looking at? We're looking at something like this. You guys remember in class, right? Because why? Because we see the word potential energy, PE, right? And the only graph you're going to remember from class that had that was this one, where, what do you remember? You remember that it's PE increasing here, and then it was what? Kinetic energy increasing at the slopes, right? You guys remember? All right. So what is that? It said, the question said, before vaporization, right? Vaporization means what? You're turning into gas, right? So it's liquid to gas. So before vaporization means you're here, down here, to the after vaporization. So we're taking it from here to right here. What's going on here? Well, obviously you can see the potential energy is increasing, right? And that's what we're going to write. So we're going to go here to 62, 60 or 62. Sorry, I think it's 60. Yeah, it's 60. You're going to say the potential energy increases. Okay. All right, 61. Determine the amount of heat required to completely melt a 50-gram sample of this molecular compound as molten pool. All right, what do we need? Amount of heat is Q. Is it not? All right. And we got M. Okay. And what else? Hey, they gave us heat of fusion right here. All right. So let's go make this shopping list. Okay. So for 61, right? Let's put, or I'm just going to put some work right here. You got Q, M, and you got HF. Okay. Now, what is the M? Was, remember, it was 50.0 grams, I think. And Q was, they wanted the amount, they wanted you to find this, right? Am I right? Yes, I am, right? And then heat of fusion is right up here at 127 joules per gram. So that's 127 joules per gram. Again, be careful. You don't want to be using, right? You don't want to be using this one. Why not? Because that's for water, right? So we don't want to be using that in this problem because we're literally looking at this other compound and they gave it to you, right? So putting that into consideration, what happens? The equation, right? Equation for this, once again, is all the way down here, right? Q equals MHF, right? So it's going to be Q equals MHF, where it's going to be 50.0 grams times 127 joules per grams. Hey, and hey, look at that, right? Grams cancels grams, giving us joules, right? So what happens? Not doing that in a calculator. I'm sorry, I'm not doing that in my head. I'm going to do it in my calculator, right? And if you put it into your calculator, what do we get? We get a value of, I believe, 6,350 joules. Now, what's sig fig? It is 3, so we're good to go. So for 61, it's 6350, just like that, okay? 62. Explain in terms of intermolecular forces why the boiling point of molecular compound is lower than the boiling point of water. That means that water boils at higher temperature, or that means this compound boils earlier. What does that mean? That means the molecules themselves are not held tight with each other. Therefore, even at lower temperatures, they start letting go and start turning into gases, right? We said this in class. So that's exactly what it is. So that means that, what are we talking about? 62, why the boiling point? This molecular compound, right? So you'd say this molecular compound has weaker intermolecular forces than that of water, right? Now, is that enough to answer it? Let's go back and take a look. In terms of intermolecular forces, why the boiling point of, that's more than enough, okay? Let's go to 63. A sodium hydroxide solution and an acid-base indicator are used to determine the molarity of an HCl solution. All right, at the time of this recording, we literally are working on this right now, so this should be your jam. A 15.0 milliliter sample of the HCl is exactly neutralized by 30.0 milliliters of yada, 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 yada. Okay, so it says identify the positive ion in the sample of HCl. Now, before you all freak out and be like, oh my God, this is acid base, right? You realize 63 has nothing to do with acid and base. It's literally asking you to identify the positive ion here, right? And what do we know? This one, you got to know how to answer that, right? It's hydrogen, H plus, right? Hydrogen ion. I think you could also get it with actually writing hydrogen ion. What if you write the word proton? But I guess it is acceptable. Now remember, in acid-base unit, we also said that H plus is same as H3O plus. So if you also wrote H3O plus, I doubt you would actually go this far. That's probably also going to be an acceptable problem, but I would stick to H plus ion. 64. Based on table M, state the color of a litmus when placed in a sample of the original HCl solution, right? So, what I'm going to do, I'm going to go here, right? I know already because, I'm a chem teacher, but let's go here and go to table litmus paper. I think I just missed it, right? Litmus paper is up here. It is. And they said litmus paper, it's right here, right? It's red to blue, right? So I know that acid equals red and base is blue. And what do we know? Original HCl. What's that, guys? That is I don't care if you're Arrhenius or Team Bronsted, that's an acid in any definition. So therefore, we know it's going to be red, right? So it's that easy, right? You just write red. So you can't get this wrong unless you don't know how to spell red. All right, number 65. Using the titration data, determine the concentration of HCl solution. All right. Are we excited? Are you excited? I am. It's my jam, right? Because we've been working on this, right? So let's do it. So I'm going to go back to the original problem, right? It's my jam, right? So I'm excited. Let's go do it. So you can go to the original problem. And what do we got? We got volume. We got another volume. And we got molarity, right? And they want the concentration, right? But what do we know? Well, first of all, it's concentration of H6, so I know that's acid. Let's go over here. Well, this molarity is base, and this is also base. That makes this your acid. Are we good? Yes? So, what does that mean? That means, I don't know if we have room to do work, so maybe I'll put the work over here, right? Because I think the answer booklet doesn't have any room anymore, right? So I'm going to write down my shopping list. Mava, mub, vub, right? And what do we got? Our this is our X, and volume of our acid is 15 milliliters, 15.0, right? And the concentrations are 0.010 molar, and then the volume of our base is 30.0 milliliters, right? And now what do we do? Use your equation, right? Mava equals muvub, right? And I know I said you should just memorize this, but it is found right here, right? There it is, right? So that's where you get it from if you didn't memorize it. All right, so now what? We're solving for MA, so therefore we're going to divide both sides by VA, right? Which will cancel out the V's, right, on the left side. So you got MA is equal to MB VB divided by VA. Let's plug in our values, shall we? So we got your MB, right, which is 0.1, 0.010, right? It's a 0.010 molar, right? VB is going to be 30.0 milliliters. And I know some of them about your screen, Mr. Again, you got to convert to liters. I'm going to show you in a second why we don't have to do that, okay? Check it out, guys. The milliliters, so let me write it, milliliters, right? They cancel each other out, and the unit for the N should actually be molarity. So we're actually okay, right? If you did convert it, it would be fine because then it would be 0.030 divided by 0.015, which is what? You know, you don't need to grab a calculator. Why is that? Because look at this, guys. What is that? That's 30 over 15, right? 15 goes into 30 twice, so that's actually going to be times 2, right? Which means your answer is times 2, like that. Okay, so that's what we're going to write, right? 0.020. So we're going to go here, and you're going to put 0.020, and we're done. All right, let's move on. So 66, let's go over here. All right. The table below shows 3 compounds that are used for medical purposes, right? Blah, blah, blah. Identify the 2 types of bonding in a compound used to make plaster casts. That's this. So we're looking at calcium sulfate. Okay. Now, I know we just got reminded this like last 2 days, but what do we know about this? We know that calcium sulfate is what? We know this is a polyatomic ion, right? So we know that this can dissociate into calcium 2 plus and sulfate 2 minus, right? So definitely what do we see in here? We see ionic, right? Because you see ionic. Now, the second part is not as easy, but if you think about it, what do you remember Mr. Kim telling you, right? That polyatomic ions by definition are what? Atoms that are bonded covalently but as a group, act as an ion. So essentially, the two are ionic and covalent, and that's it. It's that easy, okay? So I'm going to go here. What are the two? It's going to be ionic bonds and covalent bonds. Now you're thinking, hey, is it polar covalent or non-polar covalent? I don't think they care. I don't think they're going to care in this case, right? So you should be okay. Number 67, identify the noble gas that has the atoms in the ground state with the same electron configuration as a positive ion MgOH2 in the ground state. Well, in order to solve that, we got to figure out what the positive ion is, right? So what is the positive ion? Positive ion is MgOH2, and we got to break it apart, right, into ions. So what happens? Mg falls apart by itself, right? And what is it? I don't even need to finish this equation because what do we know? We know that Mg is group 2, right? And even if you didn't know, right? What just happened? Okay. Even if you didn't know, what do we know about Mg, right? What do we know? It's +2, right? So, and some of us know that, right? So it's 2 plus like that, right? So what does that mean? That means, right? And again, like, what we do know is it's 2 OH minus. But like I said, we don't really care about the OH minus because that's not the star of the show. We're talking about this guy. So the question is, what does that mean? That means Mg lost 2 electrons, right? So what does that mean? Let's go back. So if magnesium loses 2 electrons, it has total of 4 electrons, right? So if it loses 2 electrons, what are you? I'm sorry, I'm looking at the wrong one. If magnesium has 12 electrons, and if it loses 2 to become Mg2 plus, that means now it's gone from having 12 electrons to 10 electrons. Atomic number of 10, that's neon right here, right? So your answer is neon. Is that the right question? Yes. And there it is. Let's go to 68. Based on table S, I don't know what that is, determine the electronegativity difference for the bond between zinc and oxygen and ZnO. Okay? Based on table S, I think that's the table after periodic table, right? Pretty sure, right? Right. Now, I already circled it for you guys, right? Beryllium, no, I didn't. Did I? Nope, I did not. All right, so we're looking at, what is it again? Between zinc and oxygen. All right, so let's go. So oxygen is easy, right? So electronegativity difference of oxygen is that, right? That looks terrible. It's going to be right here. And then zinc, I don't know. Don't go scrolling through this. Go find zinc. I know zinc is right here. It's 30. So let's go down, scroll down to number 30. And zinc, there it is. And it's going to be electronegativity difference 1.7. Remember they said the difference? What is difference in mathematics? Subtraction, right? So essentially, in order to solve that, what do? It's the difference, guys. Can't be any easier, right? What's that? That's 1.7, right? So the answer to that is 1.7, okay? 69. During a laboratory activity, appropriate safety equipment is used and safety procedures are followed. In a beaker, student dissolves 0.1 mole of potassium nitrate in 100 grams of water at 25 degrees centigrade. The gram formula mass of KNO3 is 101 grams per mole. They even gave you gram formula mass, so you don't have to look that up, right? Here we go. Compare the freezing point of water, right, extended pressure, to the freezing point of KNO solution, right? Now, notice what I'm doing? I'm circling things, right? You really should do that. So we're comparing water to salt water, right? What do we know? Well, this is colligative properties, right? So remember, go study colligative properties, right? And we know that there's boiling point, freezing point, osmotic pressure, and vapor pressure, right? Regents really only cares about the first two, right? Which is, what are they? It's boiling point elevation and freezing point depression, right? So what do we know? We know that with salt in a solution, boiling point goes higher than that of water, and its freezing point goes lower below that of water, right? We talked about that in all the stuff like, why we use salt to melt the ice and stuff in the winter, right? So essentially, in the end, what do we say? Let's look at the words. Compare the freezing point of water, okay? So that means our water will be freezing at a higher temperature, right, than that of the solution. So you can write that the solution will freeze at a um, lower temperature. Oh, sorry. At a lower temperature than that of water, right? Or conversely, you could write also that the water will freeze at a higher temperature than that of the solution, right? It doesn't matter how you say your grammar, okay? Let's go to 7. Based on table G, classify in terms of saturation, type of KNO3 solution made by the student. All right, this one is a little bit involved. Let's go to table G. Table G, what is table G? E, F, G, and that E, F, G. Oh, there it is. This is our table G. All right, what are we looking at? We're looking at potassium nitrate, right? So go find potassium nitrate, and where is it? It's right here, okay? Now, it's this curve. Be careful, right? Now, it says 0.1 mole of potassium nitrate. We don't have mass. We do have temperature, right? In 100 grams of water. Remember what I said? You have to make sure it's 100 grams of water. We do have temperature, 25 degrees Celsius, so it's right here, right? But we need grams. We don't have grams, right? But it's easy. Why? You have this, you have that, right? So what do we know? 0.10 mole of potassium nitrate, right? You want to turn that into grams, right? What do we know? Well, moles on the bottom, grams on top. And what's the molar mass? They even gave it to us, kids, right? How ridiculous, right? So what does that mean? You don't even need a calculator. What are we doing? We're moving the decimal place one place over. So it's going to be 10.1 grams or approximately 10 grams, right? So if you're unsure, just use a calculator. But I'm going to go over here and take a look. 10 grams is about here. So where do they cross each other? They cross each other right here. KNO3 line is right here. And what do you guys think? What does that mean? We are below this curve, which means we are, that's right, we are unsaturated. This is a time where you're going to go and review and study when it is saturated and when it's super saturated, right? And precipitation and all that good stuff, right? All right, so let's go. I'm having fun. Are you having fun? You should, right? Describe a laboratory procedure a student can use to separate the original KNO3 from the KNO3 AQ solution. Well, don't overthink this, right? What is this? Remember we said this is salt, right? Remember chemistry definition of salt is anything ionic and KNO3 is ionic, right? So how do I separate salt from salt water? I'm sure you spoke about this in elementary school. What do? You evaporate it, right? So that's it. It's that easy. So you can write, does it tell you how, describe a laboratory procedure the student can use? Well, you can just write evaporation. right? They said describe it. I think that's more than enough, right? I would give you that point. But you like me, Mr. Kim. No, how do you know that? You don't know that, right? All right. Let's go to 72. A major component of agricultural fertilizer is ammonium nitrate. We actually talked about this in class, right? We also talked about how this is also an explosive, right? It is commercially produced by reacting ammonia gas with concentrated nitric acid as shown in the equation below. Oh my goodness, this is getting complicated, right? Nope. If that's coming through your head, this is the time when you say, okay, you know what? Stop, be quiet, and let's just get through this. And it's probably more complicated than it looks. All right, so let's go. Equation one, ammonia and nitric acid, blah, 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 goes to ammonium nitrate plus some energy. The ammonium nitrate can decompose to produce nitrogen dioxide gas, which is brown gas, when NO2 is produced in the sealed containers. Okay, well, you know what they're trying to do? They're trying to psych you out because they're trying to make you read all this stuff and you're like, oh my God, I'm freaking out. So I'm going to take a deep breath and read carefully again. The ammonium nitrate can decompose to produce nitrogen dioxide gas, which is a brown gas. When NO2 is placed in a sealed glass container, some NO2 molecules react to produce colorless N2O4 gas. An equilibrium system forms in the glass container as shown in the equation 2 below, and you see the equation, right? Now, be careful. Remember, these questions, not all of them have to do with what you just read. So don't get psyched out. So let's go to question number 2. State in terms of reactants and products why the chemical reaction represented by equation 1 is a synthesis reaction. Do you see how ridiculous this is? They're not even asking you to identify it. They're telling you to justify why it's a synthesis. They even told you what it is, right? So this really means what? They want to know if you know the definition of synthesis. This question is so simple, it's actually insulting, right? So taking a look at this, what do we know? Equation 1, right? Equation 1 is right here. Let's take a look. What do we get? We got, hello, 1 plus 2. Two things become a single thing. Isn't that literally definition of synthesis, right? Where two simple things make one single complex thing, right? That's literally what we're going to write, right? We're going to write two simple things become one complex thing. Yeah, I know it sounds like Dr. Zeus, but we're done, right? That's how easy this one is, right? So again, now you're feeling silly because you freaked out over nothing, right? All right, so let's go to 73. On the labeled axes in your answer booklet, draw a potential energy diagram for the reaction represented by equation 1. Now, again, guys, I've only told you how to draw this two different ways, right? Potential energy diagram. You remember what I drew? I drew one that went like this, and I drew one that went like this, right? And if you don't know, right, you got to remember, right, which one is which. You got to memorize this, right? One of them is exothermic, one of them is endothermic, right? Now, if you go back to equation number 1, right, I'm just going to double check that it is equation 1. What do we know? Right? Energy, right? Energy is on what side? Reactant or product side? What do you think? It's on the product side. If the energy is on the product side, remember, that means that it's lost. That means this is exothermic, right? Which equation is exothermic? The one where you lost energy from left to right side of the graph? That'd be this guy. We're done, guys. It's this easy. All right, so I'm going to go here. What am I going to do? I'm literally going to draw a random exothermic graph, and this is how easy this one is, okay? Let's go to 74. Compare the rate of forward reaction to rate of the reverse reaction in the equilibrium system, right? Represent equation 2. What did I literally tell you in equilibrium system, right? I did the example of Mr. Mr. Van X kids moving chairs in and then you guys moving chairs out. I said when we're at equilibrium, that means what? For every 2 chairs come in, every 2 chairs go out, which means what? The rate is going to be, what is it? That's right. It's the same. Okay? All right. So I'm going to pause right here. And we're going to resume in a second, okay? Hey guys, I'm back. There was a 9th period, and for some reason, a lot of kids showed up. So let's continue and finish this off. 75. All right, this is organic. So I'm not going to expect you to know how to do this at the time of this recording, but hopefully later, if you're watching this, this should be doable. But on top of that, it's actually not that bad. So let's think about this, okay? So it says pentane, hexane, and heptane. So you know what? There is a table of prefixes. And this is the thing I told you, like, it's the dumbest thing ever because they give it to you here, right? Organic prefixes. And it's the only time when you need it, right? So there are prefixes right here, right? So if you follow this, you'll understand that hex is, pentane is 5, 6, 7, 8, right? Are parts of gasoline. Structure formula below represents straight chain molecule of a pentane. So that's, as you can see, that's 5, right? According to pent right here, right? So as you can see, you got 1, 2, 3, 4, 5. And then obviously later on when you watch this, we're going to have covered organic. But the fact that it's ane, right, means right here, it's an ane, right? Ane means all of the carbon-to-carbon bonds are single, whereas an ene is a double or ine is could be a triple, right? So we know that's all single bonds. So it says state the number of hydrogen atoms found in the molecule of hexane, right? Be careful. Don't go counting this because this is wrong. Hex is 6, right? And it's an ane. So to draw this, it's going to be 1, 2, 3, 4, 5, 6, all connected by single bonds. And then after that, there's hydrogens so that carbons all have an octet, right? So if that's the case, what do we get? You get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 places where hydrogens can attach, right? So therefore, it'd be 14 hydrogens. And let's go write that in, right? So it's 14 is your answer. State in terms of carbon-carbon bonds why octane is a saturated hydrocarbon. That's, again, a definition thing. Saturated hydrocarbon means it's a carbon-to-carbon, all single bonds, right? So in saturated hydrocarbon, all carbon-to-carbon bonds are single bonds. Okay? That's a definition. Number 7, draw structural formula for a straight chain molecule of heptane. Hept is what? It's 7. So you're going to draw 7 carbons. So let's go. So you're going to go here. You're going to draw 1, 2, 3, 4, 5, 6, 7 is heptane, and it's a straight chain. So you're going to do this, okay? So carbons all have an octet, right? Do that. Now, you could go ahead and put H's all around, but this right here like this is completely acceptable, right? But you can go waste your time and put H's in, completely unnecessary, but you can do that as well. So the way it was before I put all those H's, it is completely acceptable correct answer, or you could also go ahead and fill in all the H's, and that's how you do it. 78. Let's go. Oh, what is this? This is power source, electrolytic. Not only that, what do we know, right? This is my jam, right? Well, how do I write that? I'm excited because I know how to do this, right? Let's go. Chlorine gas and sodium metal are two valuable industrial elements that can be produced in a electrochemical cell by electrolytic reaction. In the reaction, liquid sodium chloride is separated into elements of electric current. The simplified diagram equation below represent the process. Okay. So let's go. State in terms of energy. Why the power source is required for the cell to operate? Well, duh. What does that mean? Once again, it's a definition problem. What do we got going? It's an electrolytic cell, right? Why do you need a power source in an electrolytic cell? Because What do you say? Electrolytic cells, lytic cells are non-spontaneous chemical come on oh geez, chemical. Oh, computer wants to go home because day's actually over. It's actually way past ninth period, end of ninth period, right? Therefore, requires, you know what I'm going to write soon after this? External electrical energy to force it to happen, right? You all good? All right. So something along this line is probably what's useful, okay? 78's done. 79, state the number of moles of electrons lost when 4 moles of electrons are gained in this reaction. This is a trick question, right? Because they're asking you to, go crazy over this. But I said this many times in this class, right? Remember, the number of electrons lost by oxidation half cell should be equal to the number of electrons gained by the reduction, right? So therefore, what do you think the answer is? What do you guys think? It's 4. It's that easy, okay? So it's 4 moles, right? Loss. Oh, and you know what? Not that it matters. I don't think they're going to care, but let's keep the sig figs the same. All right, let's go to 80. Determine the change in oxidation state that occurs for chlorine in this cell. You're like, oh no, what do we know, right? Go, I don't know what to do. Hello, go over here, right? What is it asking you to do, right? You remember? Rule number 1. And then after that, what do we got? Chlorine is halogen, so it's going to be -1. That's going to be +1. And it says for chlorine. So essentially, we're going to go from this to this, right? So what is it? -1, 2, 0, right? So easy. So it's going to be going from -1 to a 0, okay? All right, we are almost done. And now it's going to go to nuclear. And I know that at the time of this video, we haven't covered nuclear yet, but I'm going to show you. If you watch this before we cover it, you're going to see how easy this is, okay? All right. I'm not even going to read this right now because you know what? I'm going to go home. I want to go home and play with my dog. So let's go. Using the graph, determine the half-life of TH230, right? What is half-life, right? Half-life of the pizza is the time it takes for Justin to finish half of his pizza pie. So you start with so much and you end up with half, right? Well, take a look, guys. We start with 40. Where do you think half point is? It's going to be 20. Right? So if Justin started with 40 slices of pizza and then he eats half of it, you're going to be left with 20, right? So the question is, that is your halfway point. So this is your time, okay? It's that easy, all right? So what does that mean? We just have to figure out what the heck this is. Notice, these are all 10 to the 5th, right? And it's 1 here and 2 here, and it's 1, 2, 3, 4. It's 4 pieces left. So therefore, what do we know? That's from 0 to 1 times 10 to the 5, right? So therefore, what do we know? This is 3/4, or this is going to be, let me zoom in, 0.25. This is going to be 0.5. This is going to be 0.75, and that's 1, isn't it? So the answer is actually going to be, right, 0.75 times 10 to the 5th, right? You see that? Because I'm looking at 1, 2, 3, right? And subdividing it. Now, if you want to freak out over this, you're like, oh my God, Mr. Kim, like that's an improper scientific notation. That's fine. But apparently, this is A-OK. Okay? It's perfectly good answer. If you do want to write it as a proper scientific notation, 0.75 is 7.5 times 10 to the -1 times 10 to the 5th, right? Right? which is going to be 7.5 times 10 to the 4. Either you write this or you write this, it's going to be acceptable. And just so that you guys are not freaking out, I'm going to write it the way 0.75 times 10 to the 5th years is our answer. Okay? Number 82, determine the fraction of the sample that remains unchanged after 2 half-lives. This is how easy nuclear is. You don't need any of this information, right? Remember, it's 2 half-lives, right? Definition of half-life is the time it takes to eat half and leave behind whatever's left. So let's think about it. You start with a whole. After 1 half-life, how much is left? Half is left. After a second half-life, what happens? You ate half of the half. What's half of half, right? That's a quarter, right? Guys, we're done. That's the answer, right? So it's going to be 1/4. It's this easy, folks, right? Let's go to 83. Compare the penetrating power of beta particle to penetrating power of alpha particle, decay particle from an atom. I've actually said this, even though we didn't do nuclear, back when with the Rutherford School foil experiment. Alpha particles are big and chunky, right? And I said big fat guys can't penetrate through as well as tiny little guys. Beta particle is also known as electron. They're tiny. So therefore, what we know is beta particle will penetrate much farther than an alpha particle. Okay, so that's what you're going to write. So let's say beta particle will penetrate further than an alpha particle. Okay? This, I know if you're watching this before we cover this unit, you're going to be like, what does that mean? It's a simple definition, right? All right. Next, complete the nuclear equation in your answer booklet for the decay of U-238 by writing the notation for missing product. Again, time of this video, we haven't covered it yet, but I'm going to show you how easy this is. It goes back to the conservation of energy and mass, which tells you that numbers on left and right side of the equation must be the same. Look, the total number on the left side right now is 92. Left side is only 2. So therefore, how do you make this equal? This thing better have a 90 on the bottom, right? Because 90 plus 2 is 92. Same goes for the top. 238 is on the left side. And on the right side, you got a 4. So 4 plus what gives us 238? 234, right? Like that. Now the question is, who is this guy, right? Remember, if you don't know, take a look. Uranium, 92, helium 2, right? Is that correct? Let's go to our reference table and take a look. And if you see here, sure enough, right? Uranium is 92 and helium is a 2. Do you see that? So the bottom number identifies who they are. And just do detective work. That means who's 90? Let's go look up 90. 90 is right here. And that's TH, or thorium. So you're just going to look it up and write down thorium. And it's this easy, guys. Okay, let's go to 85. 85. Explain in terms of elements why the nuclear decay of 234 to 237 is considered transmutation. You know what trans is? So when you go from male to female, female to male, right? What does it mean? You change identity. That is the same exact thing, right? So that's what you're going to write and hope that Trump and his people don't come after you for saying it. But what is the actual answer? I know I sound like I'm joking, but you would say the atom changed its identity. I know it sounds like I'm making this up. It's not. That's literally what transmutation is, right? Mutation means what? Change from bio, right? Trans means it's going from, it's losing identity. It's changing identity. That's literally what that means, all right? All right, easy peasy. And then what happens? What's next? Oh my goodness. What happened, guys? We're done. we are done, and this test was that easy. Okay, so I hope looking at this, you find this easy, one, and two, any things you got wrong, you're going to go and start reviewing it, right? And then therefore, after that, when you're done, come back to this and then try to see if you can re-answer this question, right? All right, I hope this was helpful to you guys. Thanks for watching.